Welcome to Maths with EJD. In this video, I'm talking about inverse hyperbolic functions. So, inverse hyperbolic functions are the inverse functions of the hyperbolic functions. I mean, that sounds redundant, but that's what we have. So inverse hyperbolic functions are the functions of the hyperbolic functions. So if you remember, I mean, if you check the playlist on calculus, there was a part I was talking about functions, and we got to that part where we talked about inverses of functions, so that we can find the inverses of functions, right? So inverses are important. They are important in calculus and appear in various mathematical contexts. They are important in calculus and appear in various mathematical contexts, especially, especially in solving equations, and integrals involving hyperbolic functions. Okay, so let's define these inverses and see their graphs too. So let's say definitions, definitions, and graphs of inverse hyperbolic functions. So first of all, let's talk about the inverse hyperbolic sign, inverse hyperbolic sign. That is arcsinge, arcsinge x, arcsinge x. So the definition is such, okay, uh, so okay, let me just do this. So the definition, it's this arcsinge x is equal to y, such that such that singe singe y is equal to x. I mean, that makes common sense because from here, this is singe, arcsinge, right? X is equal to y. So if you take the singe of both sides, so you have singe of arcsinge of x equals singe of y. So this cancels out. So that at the end of the day, singe y is simply equal to the x that is left here. Okay. So that's that. So then it has a logarithmic form. Logarithmic form. So the logarithmic form is this, that arc singe of x is equal to ln x plus square root of x squared plus 1. That's the logarithmic form. And the graph, let's talk about the graph. Of course, in a moment, we are going to visualize that. The graph of arcsinge x. So the graph of arcsinge x, arcsinge x is similar to the graph. So similar to the graph of ln x, but stretches it differently, stretches differently as x increases, or decreases. So it means it will be important to compare it with the graph of ln x. So let's see what the graph looks like. So then that takes us to Desmos. So we're talking about arcsin x, arcsin x. So see what the graph looks like. So it looks like it's coming from somewhere. It passes through zero and it merges. And as x increases on both sides, it's the gap between it and the x-axis is wider. So since it looks like Linux, let's see what Linux itself So look at Linux. Linux is only coming, so it's coming straight from the line and then it emerges and then goes that way. So the stretching is different. So that's the closest thing we can compare that to. Okay, so that is arcsin x. So let's go back and let's go on to the next, which is arcosh x. So number two, we have two. Let's talk about hyperbolic, inverse hyperbolic cosine, which is arcosh x, like that. So talking about the definition, we have that arcosh x is equal to y, just like before, such that cosh y is equal to x. And then we see the logarithmic form, that is arc cosh x is ln of x plus, that's natural logarithm of x plus square root of x squared minus 1, like that. Okay. For the previous one, okay, there's no restraint on that. But of course, since we have a square root, so a condition is necessary. It is important that x is always greater than or equal to 1 to guarantee that this does not go indefinite. Okay, so x has got to be greater than or equal to 1 so that we can always have the square root defined always. It wasn't required for this because there's no possibility of of it going negative, no matter what x is, even if x is negative. Okay, so talking about the graph now, graph. So the graph of arccosh x starts at x equals 1, starts at x equals 1, because x cannot be less than 1 because of the square root. So it starts at x equals 1 and increases rapidly. It increases rapidly for larger x. It increases rapidly for larger x. So let's visualize that on Desmos. So, okay, well, to see it better, we can remove this too. So we focus on arccosh x. Okay, so you can see it's starting from 1 and then it goes like that. So it's looking a bit like a logarithm functions somewhat, but then it grows, it keeps growing like that. So it cannot start anywhere before 1 because of the square roots, I'm sure. Okay, so let's move on to the next inverse hyperbolic function. So this is, I believe that's number 3. Number 3 now is inverse hyperbolic tangent. Inverse hyperbolic tangent. That is arc times x, like that. So that, first of all, talking about the definition, uh, it is such that arc times x is equal to y, such that times y is equal to x. So, and the logarithmic form is arc times x equals 1 over 2 ln 1 plus x all over 1 minus x. Yeah, this has some uses, you know. I mean, I remember trying to get, I was trying to normalize a particular data, and this became really useful. You know, it's good for, I think, normalizing data ranging from probably, is it 0 to 1 or minus 1 to 1? So something like that. So this is really useful in that context. So, and of course, here you have to see that x has got to lie between minus 1 and 1. So minus 1 is less than x and x is less than 1, meaning that the absolute value of x has to be always less than 1 because of the particular definition of the expression, you know. So, and then let's talk about the graph. The graph of arctange x. So the graph of arctange x approaches infinity as x approaches plus or minus 1. Okay, so let's see what that looks like. Arctange x now. So this can go. So we have arctange. Oh, sorry. Arctange x. Okay, see what that looks like. So so it's about the y-axis like that. So, you know, and you can see that it is restricted between minus 1 and 1. So you can see so it's confined between minus 1 and 1. So that's arctange x. So that takes us to the next one, which is inverse hyperbolic cotangent. Inverse hyperbolic cotangent. So that's number 4. Inverse hyperbolic cotangent. So that is arcosh x. That. So we have the definition. So arcosh x is equal to y, such that cosh y is equal to x. And then we have the logarithmic form, which is arcosh x is equal to 1 over 2 ln x plus 1 over x minus 1. It's looking exactly like what we had before. What's the difference here? X plus 1, x minus. Oh, that was 1 plus x, 1 minus x. So this is x plus 1, x minus 1. Okay. So, and then here we have the graph. We have the graph of arccosh x is undefined. It is undefined between minus 1 and 1. So it means that it will jump this range and just have definition before minus 1 and after 1. But resembles the graph. It resembles the graph of arctange x, which we just saw, outside of this interval. Outside of this interval. Okay, so that's for arccosh x. Let's see that. Arccosh x. So arccosh x. Okay, so it's I think this is what we call asymptote or something like that. So it's never gets to 1 or -1. So it's like it is asymptotic around -1 and 1. So you see that symmetry around that region. Okay, so we go on to the next, being I believe number 5 now. Number 5. Let's talk about number 5, which is inverse hyperbolic secant. Inverse hyperbolic secant, which is arc sesh x. Then by definition, same format, by definition, it is actually arc sesh x is y, such that sesh y is equal to x. Then you have the logarithmic form, which is arc sesh x equals natural logarithm, that's ln 1 plus square root of 1 minus x squared all over x. And 0 lies between x, 0 less than x less than or equal to 1. So, and then talking about the graph of arc sesh x starts at x equals 1 and decreases rapidly towards 0 as x approaches 0. Okay, so let's see that arc sesh x, arc sesh x. Okay, so you can see it starts from 1, and then I mean this is interesting. So it starts from 1 like this, and then it begins to it goes rapidly towards 0 along the y-axis. So has such an interesting behavior. Okay, let's go back to the next one, should be number 6 now. Number 6. So for number 6, we have, number 6 is inverse hyperbolic cosecant, cosecant. So that is arc cosesh x. So that for definition, we have arc cosesh x, which is y, such that cosesh y is equal to x. So, and in logarithmic form, we have arc cosesh x equals ln 1 over x plus square root of 1 over x squared plus 1. Okay, no restrictions in this case because it's all positive. And then we have the graph. The graph of arc cosesh x is symmetric. Around the origin, rapidly decreasing as x moves away from 0. Yeah, let's confirm that. Arcosh x. So we have arcosh x. Okay, looks a bit like what we a bit like is he I think we've seen something like this. That one that is always running away from 1. That's not defined between -1 and 1. Yeah, that's the arc cotangent. Okay, arc cotangent. Except that this one now, it's not, it doesn't have the same 1 behavior, but it doesn't ever get to 0 actually. So with that, we see all the graphs now. So let's move on to something else. Let's move on to integrals involving inverse hyperbolic functions. So integrals, because okay, before I even go to that, derivatives actually. So let's talk about the derivatives of inverse hyperbolic functions. So that's us differentiating them. So the derivatives of inverse hyperbolic functions are essential for various applications in calculus, especially in solving integrals. So first of all, we talk about d dx of arc sin x. And that derivative is 1 over square root of x squared plus 1. So for you to know, to get that right, you already have the logarithmic form of each one. So just differentiate, that's all. So for this now, see what we have. We have arc sin of this. So to differentiate this now, we already know that this is log, right? So when you're differentiating anything log, so it differentiates the expression itself. So it's like you have, okay, I guess I just want to demonstrate that. Maybe that's the only one I'll do, just to clarify that. So we know already that arcsine of x, so we have arcsine of x to be equal to ln of x plus x squared plus 1. That's square root of this now. So d dx of arc sin of x is actually d dx of ln x plus square root of x squared plus 1. To make things easy, right? We can say this is simply, to make it easy, we can say this is d dx of ln x plus x squared plus 1. So it's raised to power half. So it's easier to handle this way. So, and when you're differentiating the log of a function, right? So the rule is differentiate the function, the function itself and put it over the original. So differentiate x, that's 1, plus differentiate this, that's function of a function, bring down the power half, differentiate inside, you get 2x. Then the original function you have reduced by 1. So that is x squared plus 1 raised by half minus 1, which is minus 3 over 2. And all of that now over the original, that's x plus x squared plus 1 raised by half. Now, if this is confusing to you, you may want to refer to my playlist on basic calculus. So all of this is well dissected there. So you can cancel this out. So we have 1 plus x into x squared plus 1 raised by minus 3 over 2. Then all this over x plus x squared plus 1 raised power 1 over 2. Now, think simplifying all this. Okay, this is, I have bought job. So like they say, this is 1 plus, so this is x, okay, I'm trying to see. Okay, this is actually x times um so x squared plus 1 raised by minus 3 over 2 is actually 1 over x squared plus 1 raised power 3 over 2, something like this. So that is all over 1 plus x squared plus 1 raised power half. So next we have 1 plus x all over the square roots, because of these two down, that's square roots of x squared plus 1 of the cube of these three. I mean, of that now, all over 1 plus x squared plus 1 raised power. Okay, I can put the roots there for that too, right? So that's plus square root of x squared plus 1. So, of course, we can take the LCM of the top. So we have the LCM to be square root of x squared plus 1 cube, and that is 1 goes here. So we have square root of x squared plus 1 cube plus this cancels this, so we just have x down there. Then all of that now divided by what we had there before. That's 1 plus, is it 1 or x? Yeah, it should still be x. This doesn't change, it is still x, sorry. This is x. So this is still x plus square roots of x squared plus 1. So we can do the division. So this is square roots of x squared plus 1. Of course, that's the cube of that now, plus x. Then all over square roots of x squared plus 1, the cube of that, then divided by this, that is times 1 over, okay, that's divided by this, right? So that's times 1 over x plus, man, this is serious, x plus square root of x squared plus 1. So let's see what happens. So that means we have x plus root x squared plus 1 raised to power 3 divided by, so x multiplied by this, so that's x square root of x squared plus 1 all cube, okay, plus, okay, this is power 3, then you have an additional one now, so that will be square root of x squared plus 1 all raised to power 4. That is this multiplied by this now. So now let's see what happens. Here we now have, so I guess we can factorize. So we have x plus square root of x squared plus 1 all raised to power 3 divided by, you see this is common, so we have square root of x squared plus 1 all raised to power 3 is common. All of that into x plus 1 of this will remain square root of square root of x squared plus 1, right? Now this is getting too complicated, and I would rather, I guess I'll have to leave this so that I don't get bogged down by it. So I hope I've not made any mistake anywhere. Okay. So at the end of the day, I mean, I guess I just want to go. I hope I've not made any mistakes. So if you find any mistake, please tell me in the comments. But I don't want to waste time with this anymore. So, in short, we know that when we differentiate, uh, the ddx of arcsinch of x gives us 1 over square root of x squared plus 1. So this is what I was trying to arrive at, but somehow it's taking too long to get there. Okay, so let's move on to the next one. That's number 2. ddx of arcosh of x is now 1 over square root of x squared minus 1. And of course, there's an imposition that x has to be greater than 1 for sure because of the square roots. Then, does the square root really matter? Yeah, it has to be. If it is 1, then that place will be undefined. Yeah, so because of the square roots for sure. Then we have 3, we have ddx of arctanh of x, and that is 1 over 1 minus x squared. And the condition is that the absolute value of x must be less than 1, meaning that x must lie between minus 1 and 1. And number 4, we have ddx of arcosh of x. And that is same, 1 over 1 minus x squared with the same condition. X lies between minus 1 and 1. Then we have number 5, that's ddx of arc sesh of x. And that is minus 1 over x root 1 minus x squared. And that is 0 less than x less than or equal to 1, like that. And then we have number 6. Number 6 is d dx of arcosh of x. Again, that's minus 1 all over absolute value of x multiplied by the square root of 1 plus x squared, like that. So we have all that. And that takes us to the integrals involving inverse hyperbolic functions. Integrals involving inverse hyperbolic functions. Inverse hyperbolic functions. So let's start with this. So we have the first integral of 1 over square root of x squared plus 1 dx. Anytime you see this integral, you can, you need substitution involving sinh. So arcsinh of x plus c. So that's that. Any integral that is 1 over square root of x squared plus 1. So it involves sinh. Then, secondly, you have integral of 1 over square root of x squared minus 1. So dx, that involves cosh, arccosh x plus c. Then 3, if you have any integral involving 1 over 1 minus x squared dx, that involves arctanh of x plus c, right? Then we go again. Number 4, any integral involving 1 over x root 1 minus x squared dx, that will be equal to minus arcsinh x plus the arbitrary constant c. So we have these 4 integrals involving hyperbolic functions. So these examples and explanation should help in understanding the properties and applications of inverse hyperbolic functions. So, I mean, it can be really tedious. So, thank you for listening so far. See you next time. But of course, be sure to subscribe if you haven't done that already. And of course, hit the notification bell so you can get alerted anytime a new video is released. And of course, be sure to comment, like, and share with others so that more and more people can get to learn these things. Bye.